Assalamualaikum and good day, Judge. I'm Rohana Binti Hasan from UTHM Universiti Tun Hussein on Malaysia under the supervisor of TS Dr. Ahmad Fateh bin Mohamad. No, my team is Adibah Binti Ahmad. Today, I will present our innovation titled Edge and Fault Detection for PB Farm with Proactive Alert, a small system that detects solar farm early using artificial intelligence of the edge. Large-scale photovoltaic farm often face hidden inverter fault that reduce power generation. Manual inspection are slow and reactive, not predictive. This lead to energy losses, highest maintenance costs and efficiencies operation. Malaysia targets 70% renewable energy by 2015. So proactive and intelligent fault detection is essential. Our motivation is to shift from reactive maintenance to proactive AI-based fault detection at the edge. This project has three main objectives. The manual method use a simulated dataset from a 2050 kilowatt photovoltaic farm for fault detection testing. Data inputs include irradiance, temperature, voltage, current, and power. If equal, power is below 90% of current drop, more than 25%. The system classified is a fault. However, this process is manual, time-consuming, and not suitable for real-time operation. This slide shows the dataset source used in the manual baseline fault detection. The data come from a public fault detection dataset in photovoltaic farm, simulating a 2050 kilowatt PV system. We manually observe inverter parameter including voltage, current, and power. From this value, we calculate the expected power and compare it to the equal output to identify whether the condition is normal or fault. This table summarizes the manual fault detection process. We use two key thresholds. First, if the output power is below 90% of expected, it's a potential fault. And second, if DC drop more than 20%, the system marked as a current drop fault. By combining both, we classified severity into normal, wash, warning, and critical level. The manual process helped us crack a fair baseline for the comparison with the end model. This graph highlights the severity level between power deviation and current drop. When both the power output and current drop below the threshold, we know the system is entering a serious fault stage. The visualization clearly shows the early detection is important before energy loss occurs. This slide presents our proposed HANN architecture for fault detection. It starts with inverter data, irradiance, temperature, voltage, current, and power. Here is the overall ANN architecture. The input layer collect inverter parameter. The hidden layer process data using the ReLU activation function, and the output layer predict the fault probability between 0 and 1. The output is the mapped into 4 severity level: normal, wash, warning, and critical. This system transforms reactive maintenance into proactive and intelligent fault monitoring. This diagram explains how the NN alert system works step by step. This slide shows a performance comparison between the manual fault detection method and the NN model. We can clearly see that the NN achieves much higher result in every metric. The accuracy increased from 0.17 to 0.76, recall improved from 0.01 to 0.91, and F1 score rose from 0.01 to 0.87. This present gains of more than 8,000% improved compared to the traditional approach. This is the coefficient metric for the ANN model using test data. From 600 total sample, the model achieved an accuracy of 92.3%, a precision of 91.9%, and an F1 of the 95.2%. The green box show true fault detection, while the blue box show false negative that we successfully minus. The proven that the model not only detect fault correctly, but also reduce fault alarm efficiently, ensuring accurate and stable fault classification. This slide illustrates the NN proactive alert timeline. The NN model continuously monitor and the inverter and provide a real-time notification before major flow rate happen. This ensures early maintenance. This slide explains how deploying the HANN model improves the return on investment for solar farm. It uses a low-cost microcontroller that runs without expensive SCADA system. To conclude, traditional method rely on manual threshold and are reactive. Our proposed HANN model offer proactive fault detection through machine learning. In the future, we plan to integrate this model with IoT dashboard, expand it for predictive maintenance, validate it through real field tests at UiTM Solar Park 2, and develop a commercial plug-and-play edge AI model for industry use. The novelty of this research lies in using edge-based ANN fault detection that depend only on inverter data, no SCADA or external sensor required. It benefits user by reducing time and preventing large energy losses. For the community, it supports Malaysia renewable energy goal under my RER and NETR 2050. It also offers industrial potential as a deployable training module for university and polytechnic. Thank you for your time and attention.